We're now going to take a look at refining and combustion, which are two processes that happen often in industry. And it's a good thing to know going into a diploma because they do often bring up these types of processes in their example style questions. So we're just going to go over this quite briefly to look at some refining processes in terms of oil and gas, and then combustion as well. So the first thing we'll look at is called ethane cracking. Now, cracking is an industrial process where we take larger hydrocarbon molecules and we break them down at higher temperatures. So we sometimes call this dehydrogenation. Now, in terms of our example here, we're looking at ethane. However, cracking can be done to break down more, even larger compounds into smaller compounds that we are more manageable and used more frequently for different things. So if we look at something like ethane, we have our 2-carbon alkane, and we add heat. Through that, we have dehydrogenation because we have hydrogen as a product, and we have ethene formed. We use this process quite a bunch in industry because we have a lot of industry that's based off of polyethylenes or polyethylene. Okay, so we use this as a byproduct of our ethane to create plastics and things like that from ethene as a monomer, which we'll get into in a later lesson here. But again, cracking is a very important industrial process in terms of our refining of a oil product or a natural gas product. Okay, so cracking is that breaking down of large molecules to smaller ones. In terms of refining, there's a lot of things that go on in natural gas and oil refining. One of the things that we do see in natural gas and oil refining is this thing called fractionation or fractional distillation. And essentially what it is we can separate different components of our crude oil, okay, by using a machine that essentially boils or it adds incredible heat to our crude oil sample, where we can separate out different components of that crude oil. So fractionation uses the fact that these entities have different boiling points to separate them out from the crude oil. So our heat is essentially at the bottom. This is our distillation tower here that I have on the side. Okay, so our distillation tower is this long, tall thing. And we have the heat at the bottom. Okay, so we have, oops, that's not a very good color to see right now. Here, let's change that up. So we have heat at the bottom. And what happens is when we add this heat, okay, we are boiling our entities at the bottom. Now, essentially what happens is the entities that have a lower boiling point boil off first and they rise. So because it's a gas and because there's hot air, they rise towards the top of your fractional tower. So things like gasoline vapors, LPGs, and we'll talk about what LPGs are in a minute, okay, naphtha, kerosene, diesel, oil, and heavy oil, and then this would be essentially like asphalt sitting at the bottom here. So what we see is based on our boiling points and based on the fact that this is hot air and hot air rises and the components of that will rise, we can separate these things off. So we'll see that at the top of our tower, we have a pipe that's going to be pulling off all of your gasoline vapors and LPGs. And essentially there's another, it'll most likely go to another level of purification where we can separate different components out there. Then we have naphtha with a reformer that we form gasoline. Kerosene we use for example, jet fuel. We have something that we can use to crack our ethane potentially, and we get gasoline, motor gasoline, jet fuel, some aviation fuel based on alkylation, things like that. So we have this fractioner that we can use to separate the components of our crude oil. Now, following that crude oil extraction, we can also use a solvent extraction. And essentially what a solvent will do is we can separate specific organic compounds based on polarity and things like that to pull a specific organic from a mixture. Now, we often do this when we have waxes or things like that that we need to pull out of our usable organic compound. Now, again, I use waxes as the example because often when we pull oil out of the ground, it is very, very, very waxy, paraffin wax, and wax is a hard compound to deal with. So if we use a solvent to pull out our oil out of that wax, then the wax can be reused. Often we use waxes for different things, but we definitely are looking to get that oil out of the wax. So that is something that we see often. So if we take a look, this is again just a different image of a fractionation tower or fractional distillation. Again, you have cooling going upwards. We heat at different boiling points. These things have the highest boiling points. And LPGs are, again, that liquid petroleum gases. Okay, and we see condensation, obviously, that would happen there. So again, we heat it at the bottom. Our heaviest things stay towards the bottom, like our asphalt, our waxes, our oils. Then as we get up higher, we get kerosene and jet fuel, gasoline, and lighter products towards the top. Now again, notice how as we go down our list here, we have a lower boiling point, okay? And as we go down, we get higher and higher boiling points. So we have waxes that boil at above 450 degrees Celsius, and then these unvaporized residues, which is asphalt, things like that, boil at around over 500 degrees Celsius. So you'll see how this would be an efficient way to separate our different components, and we can be very specific as to where what we use as our cooling method to really pull off the entities that we need for each of these steps. We can make specific boiling temperatures or boiling points to pull those off at that temperature. Okay, so we do see that, and as we go through, we can see that gases, we can use fuels for cooking and heating homes. That's like methane, things like that. Naphthas, we have cleaning solvents, naphtha gas, camping fuels. Okay, then we have our automotive gasoline, jet fuel, diesel, things like that. Then we have our furnace oil here. Lubricating oils, cracking stock is our heavy gas oil. Greases, okay, is a little bit lower. Paraffin waxes, again, is those that wax that we pull out. Again, we use wax quite a bit in terms of polishes and candles, things like that. Sometimes we even use some natural waxes in cooking. And then we also have our asphalts, tars, things like that we have at the very bottom. And obviously that's used for paving roads and sometimes even roofing to waterproof roofs. So very different components that we can pull out from this fractionation tower. Some other industrial processes, I just have the general gist of what's going on in these things. We talked about cracking already. We see that we can have catalytic cracking, and essentially we use a catalyst of some kind to break down these large molecules into smaller molecules. Often we get carbon as a residue, which sometimes is unfavorable. So we can also do something that has hydrocracking, where we add hydrogen to our large molecule to create smaller molecules, and generally we'll break it up into two smaller molecules without any carbon remaining. Again, that is slightly more favorable than having carbon as a residue. Then we have catalytic reforming. Now, reform. Okay, we reform a molecule. So we're taking an aliphatic molecule, again, an alkane, alkene, or an alkyne, and turn it into an aromatic molecule plus hydrogen. Now, some of these aromatic molecules, although they are potentially carcinogenic for us, they can also be used in industry or for combustion, things like that. Sometimes they're a little bit more effective in terms of combustion. And then we have a process called alkylation. Sometimes it's called isomerization, which is just a structural isomer. We're taking an aliphatic molecule and we're turning it into a branched aliphatic molecule. So we're taking aliphatic and we're just making it more branched. We're adding more branches. Now, the reason that we might want more branches is to change the boiling point of a compound, as well as if we're talking about gasoline, if we have a more branched isomer, we have a better octane number, which we'll talk about next. So again, octane number, octane number is essentially the number that you see at the pump when you're fueling up a vehicle. So you'll see premium gasoline maybe with an octane number of 98, and regular gasoline maybe with an octane number of 88. And essentially it's again just a percentage of its octane rating, and we have from 0 to 100%. So high octane values are essentially just a result of a more branched isomer. And what happens is if we have a more branched isomer, there's more controlled combustion of the fuel. So that is what we want. Now, low octane fuels can essentially cause knocking in the engine. And what happens is if you look at the image on the right, when you have your cylinder and your piston driving up and down the cylinder, what you'll see is that if there's a low octane fuel, there'll be a chance that there'll be spontaneous combustion, which would cause a preemptive combustion of that fuel. So the spark didn't cause the combustion, in which there would be a knocking in the engine. Whereas with a high octane value, the spark is the thing that is sure to ignite the fuel. Now, you'll see that in high performance vehicles, there will always be required a high octane fuel to prevent that from happening. And again, that's always sort of on the upstroke of that piston coming up the cylinder, and if with that high octane number, you'll prevent that preemptive igniting of that fuel, which is what we want to see. Okay, so octane number, again, just a percentage, a relative rating of branching of those aliphatic molecules. Now, we talked a little bit about combustion, and from what you know so far about combustion is that we know that we generally have some sort of hydrocarbon, okay, we have lots of oxygen present, and it always forms CO2 and H2O. This has been consistent from what we know from all the way from Science 10 and before that even. So we have a hydrocarbon, whether that be methane, let's say CH4, we have oxygen, and we always get CO2 and H2O. That has been consistent from what we know. Now, the one thing you maybe don't know in theory, but you probably are familiar with it in terms of just being at a campfire or anything like that, that we know that there's not always complete combustion. We don't always produce purely carbon dioxide and purely water vapor. So what else is produced? Well, if you know about running a vehicle in a garage, things like that, we know that there's carbon monoxide, and carbon monoxide is a very poisonous gas. And the reason that it's poisonous is it actually binds with your hemoglobin molecules way better than oxygen does, and essentially will block the oxygen from being sent to every component of your body, which can be deadly. So we know that in a car, we do have combustion. So why is it not purely carbon dioxide and water being formed? Well, what happens is if there is insufficient amounts of oxygen in a combustion reaction, okay, so just a little bit less oxygen than what you maybe need or want for a reaction, there's a few other products that might happen. Now, what you'll see is we still have our carbon dioxide and we still have our water vapor as products, but what we see is there's also carbon, solid, as a product, okay, and we also just call this soot, okay, and carbon monoxide, which is that poisonous gas. So essentially, if there is insufficient oxygen in a combustion reaction, okay, we see the ratio of X, Y, and Z to change. So as we get less oxygen, we probably shift towards the creation of a bit more soot. And if we get more oxygen, we get the creation of more carbon dioxide. Again, if we have lots of excess oxygen, we're going to get just CO2 and H2O. But if we burn even something, a hydrocarbon, such as the hydrocarbons that would be in a piece of wood, and you have it on a campfire, okay, we obviously get a remaining soot. Even that's the smoke that leaves the fire that contains carbon dioxide and water vapor. However, it also contains some of that soot present. Again, we can bring it back to their example of the car burning gasoline. We get some carbon monoxide produced as well. So essentially, with hydrocarbon combustion, we see both complete and incomplete combustion happening simultaneously in many, many combustion reactions. And essentially, you just need to know that The difference between complete and incomplete combustion is the amount of oxygen present, and that in incomplete combustion, there's 3 potential products that could be created, which is carbon, carbon monoxide, and carbon dioxide. So soot, carbon monoxide, and carbon dioxide, and always water vapor is formed in both examples. So that is something that you should be quite familiar with as well. Now these, like I mentioned initially, these style of questions, by adding in a real life example of crude oil refining or natural gas refining, things like that. The Alberta government loves to throw those type of questions in on your diploma. So to be familiar with the processes is definitely a good thing to do prior to an exam or your diploma exam. It's just going to help you sail through your exams with a little bit more ease. Okay, good luck.